quick show of hands in the room and on Zoom if you like, who has used a container before? Okay, cool. So this is going to be reasonably new content for a good chunk of the class, which is good. And we've got someone on Zoom. So about 1/3 of the in-person class raised their hand. Now where is my mouse? There we go. Okay. So what is a container? Why do we use it? What's the motivation for using container technology? So to start off with a little definition, a container is a way of packaging up our software and our dependencies such that the software can be run in numerous environments, which is quite useful because we're very rarely trying to develop software that runs in only one environment. That would be very specialized software. Most of the time, we're trying to run it somewhere where it's not being developed. Unless, of course, you're writing a little bash script, then you don't really care where it gets deployed to. So containers are really useful when we want to deploy software because our production environment is very likely to be very different to our development environment, and containers are a way of wrapping up everything that we need to run our software and taking that from our development environment over to our production environment. So we'll do a little example of why on earth is it so difficult to accomplish this? So we've got a little Python program here, and this Python program is going to calculate the maximum element of this array here, 52973. And then this, you're going to have to trust me, is going to double the maximum. It's going to double the maximum element in the array. Okay. And what I want to do is I want to take this software and I want to give it to Richard. So what we'll do is we'll just first see that, yes, okay, this is my program. And it's exactly as it says on the slide. If we run program now, we're going to get 18 out. Okay, so that should be fairly straightforward. So what we're going to do is we're going to hop over to Richard's PC. There we go. And we're going to attempt to run this code on Richard's PC. And the first thing that we see is we need to have Python installed. Okay, our very first dependency. So you may have been working on your development device for many years, installed Python, or it came with the system and you've never thought about, oh, okay, Python needs to be installed. So we'll go ahead and we'll install Python on Richard's PC. And now we've got Python. I can prove it. We've got Python 3.5.10. And if we go ahead and run this program, we'll get a syntax error. Okay. And the reason is that this version of Python doesn't support the particular feature that we're trying to use in our code. Okay, so let's upgrade our version of Python. We were on 3.5, now we're on Python 3.6. And just to confirm, yay, 3.6. So we should have this feature. If we run it now, and we get no NumPy. Okay, and that's because, and I'm sure you're familiar with this from the practicals, trying to have Flask installed, we don't have the dependency NumPy. And again, this could have been sitting on your system for years and you've forgotten it was even something you installed. So we'll just go ahead and install NumPy. Lovely. It's going to take a second. And it's going to complain, and great. Now we've installed that. Maybe we were kind and gave out a requirements.txt to list the dependencies. Maybe we weren't, so we had to work it out ourselves. But if we go and run that now, that's not the same answer that we had before. Before we were getting the double of 9, now we're getting 18, which is not great. So one of the major reasons that we like containers is because all of our dependencies are consistent. All of our software is mostly identical, and we can reliably deploy the software to other environments and have it behave the same. Now, to Python's great credit, it took me a little while to come up with such an obscure piece of software that ran differently in 2 different versions of Python. So good on them. But if you're using something like JavaScript, you're much more likely to have more success in getting weird, buggy version issues. So that's sort of why do we want compilers? So not compilers, containers. So with that in mind, what do we need to actually go and deploy our software somewhere else and make sure that it's going to run elsewhere? So the first thing we should think about is, okay, you've got all of these things installed on your computer. You've got Python, you've got NumPy. How do you know what you're depending on? So I was kind in that example in that I didn't put a C dependency, a dynamically linked C dependency that Python was using, which very well you could be relying on. So we need a way to box up our environment so that we know we're talking about only the things within this particular little clump of code. Okay, so we've got our Python environment wrapped in a little brick wall, and then we need a way to send that out to the world. And this is our container. We package up our software and all of those dependencies so that we can send it somewhere else and it can be run in this different environment. Okay, let's get into how we came to this state where we have a technology that allows us to run code across different platforms. An aside that this history is very Linux focused. The Windows world has containers. I'm not going to go into them. We'll focus on the Linux history of it because that's generally what people think of when they think containers. Okay, so all the way back in 1979, we had version 7 of the Unix operating system, and with it came a system called Kroot. Has anyone heard and or used this before? Yes, interesting. What for? Yep. Ah, interesting.
And also like the experiment like bootstrapping and another limit size so on my current machine that thing.
Okay, so a very in-depth way of experimenting with different Linux operating systems. We're isolating our Arch Linux.
I thought that, oh, I don't want to VMware or I don't want to install something in the partition. So why don't I just root into Bootstrap?
Perfect. Okay, so for everyone else, what that meant was chroot is a way to say that the files that exist are only these files. So if you've used Linux, you have the root directory, and that is the /, right? And that is the start of all of our other files. Everything comes under root. Everything comes under the root directory. Now, Kroot means change this directory to be something else, which means that we can say all of the files above this, they don't exist anymore to this process. So let's actually see what that looks like. Whoa. Okay. So what we have here is a machine where I've got my assignment solutions and my slides and everything that you would want for this course. And I want to run some code that you've written in this. Now, how do I make sure that you don't access the assignment solutions? So what I will do is I'll make a jail. So a Kroot jail means that this is some sort of isolated box where you can't, in theory, escape of. So we'll go in here and we'll say, right, what do I need? Well, if I just go ahead and make this directory, this jail directory, the root directory for some process, and then I try to run that process. So let's say we want to run ls inside, we're going to get that error. Okay, because inside of this directory, there is no ls program. So what am I going to do? Okay, well, I'll create a bin directory and I'll copy the ls command from my actual root. And so inside here, all we have is bin, and inside bin we have ls. And now what we can do is get the same error when we try to run root ls. Now, this is a bit of a lie of an error. This doesn't mean that the binary doesn't exist. This means that there are dependencies that ls is using that don't exist. So in the Linux world, what we do is we say, okay, go and list me all of the dependencies. And it says this. And so these are all the dependencies that ls is using. So what I'm going to do is cheat a little and copy a command from earlier into here, which says copy all of the dependencies that ls needs to run inside my current directory. And so what happens is I have this, I've got bin, I've got lib, inside bin I've got that, inside lib I've got that, and inside that I've got other things. Okay, so everything in here is just the things that I need to run ls. And now in theory, if I go back to my root command, yay, I can ls. Okay, and if I put slash there, it tells me, okay, at the very root, you've only got these things. If I run ls slash here, says, oh, you've got all of these things. So this ls program is running inside a root jail, which gives us a way of fencing off our programs and making sure that it doesn't talk to the outside world, doesn't rely on obscure dependencies that we've already got installed. Okay, that's enough of root. Did all that. So root has a lot of limitations. It is a file system only isolation. You can still see all of the processes that are running. You can see all of the network communication devices, which means that if I'm going to be running untrusted code in here, it's less than ideal. It is very much not user-friendly. If you were trying to develop software and you had to go and copy in all of the dependencies manually to the directory structure that you've created, you wouldn't have a very friendly time. Not very portable, so it's okay for that, but it's relying on, yeah, it's all right. It's not what we want. It's not the end goal of containers where I give you a box and that box runs my code by magic. And jailbreaking is possible. So you can escape root and you can go look at those assignment solutions. Okay. The other major technology advancement towards our goal of containers came in 1992. You get points if you can name the people in this image. I'm sure Richard's quite capable of doing so. This is the team who worked on the Plan 9 operating system, which was a reasonably clever operating system, and containers owe a lot to the Plan 9 operating system. And they introduced something called a layered file system. Okay, so what's that? A layered file system is built on layers. And what that means is you will have generally a lower level layer and an upper level layer. And of course, you can stack these layers on top of each other. But what we have is when we read a file or we ls a directory, we're going to see the projection of all of the lower layers. So we're going to see a view, an overlay that looks like all of these layers have been unioned and merged together. What you will also see is if you do any write operations on this layered file system, any lower level, any files that sit at the lower level are going to be copied up so that the original's not modified at all. So the bottom layers of a layered file system are going to be read-only. This gets important later, and there's a very useful reason for having the bottom layers be read-only. So pretend that this is our layered file system. We've got two layers here. the very bottom layer that has the file help.me and passwords.txt, and the upper layer that has diary.md. Okay, now we're looking at a merge or an overlay of these two layers. And so when we ls, we're going to see all of them. We're going to see everything that's in the upper layer and the lower layer. So this is projection on read. Copy on write looks like this. So if I write to passwords.txt, which is sitting in the lower layer, then it's going to copy that file up to the upper layer, leave the original passwords.txt unchanged, and stick a copy in the upper layer with the modifications. All right. Example of this. Okay. So what I have here, and you're going to excuse the temp for a second, is I have a directory called lower, and in lower I have what I expect. I've got my help.me, there we go, and I've got my passwords.txt. In upper, and upper exists in temp for Linux reasons, I've got just diary.md. All right, so you can see the command that was run up the top. It's mounted the lower directory on top of the upper directory, and our working directory is called merged. So inside merged, if I ls that, I get all three files that exist in both layers. And if I cat passwords, I'm going to get the exact same thing that exists in the lower layer. Now, if I were to add a password to passwords.txt into the merged passwords.txt, what I will see now is that lower is unchanged. It's got the exact same content in it. But if I look now in upper, we're going to see that we've got a new file called password. So we'd copied this up, and inside passwords, we've got what we've written to it. And if we cat the merged, we're going to see that it's got what's in that upper layer. Okay, making sense? I'm promised that these two concepts, root and layered file system, will come back to haunt you when we get into containers. Okay, layered file system, great. Yes.
So, you have to be very conscious about which way it's going to
It's automated. So if you operate in the merged directory, then you're going to make modifications to the upper layer and leave the lower layer untouched.
And like the demo that you what it's supposed to work, because you feel very intentional in the way you which files you modify and which files you didn't. Like I imagine that you could just modify passwords are here with you, just where it's located.
Yes.
Like do all of that, the upper layer, lower layer, so on and so on.
Yes. So in theory, you can mess around with the layered file system and you can update the lower directory manually, and you can sort of, well, not really break it because it's still going to be there, right? You've just worked around the write-only, the read-only perspective. But yeah, in general, what we do is we try to hide away that lower level. We make it read-only, and then that prevents people from actually going and fiddling with it, and allow our mounting to do the copy on write for us, and then we can leave our lower level protected. Okay. All right. So back to the history. In 2002, we're getting closer to today. The Linux kernel version 2.4.19 introduced our very first namespace. So a namespace is a way for Linux to isolate things, which is what we're talking about. We're talking about containers, getting things isolated and locked away. So Linux is composed of a whole bunch of namespaces. So in 2002, they introduced the first one, which is the mount namespace, and this works conceptually similar to Groot. We're allowed to isolate the file system with this mount namespace. And then all the way, you can ignore the ones in 2006 for now. In 2008, we solved this problem of processes are still accessible and you can still see them in our jails by introducing a process ID or PID namespace, which allowed us to isolate away processes using namespaces. And then in 2009, we had network namespace that allowed us to isolate network drives, and then user and then control group. And along that way, while we were adding namespaces to Linux, we had a whole bunch of people working on what would probably later become a container. They were looking at just isolating things, okay? And so during this process, there were a lot of attempts at building a container technology, and a lot of them were very successful. But up until we got to the sort of network namespace, before then, you had to write patches to the Linux kernel. So you had to modify the kernel because it didn't have support for isolating in the way that we would want. So the very first container technology that didn't rely on changing the Linux kernel was Linux containers around 2008. So if we look at this, they didn't have networks properly isolated, but they did have process IDs isolated, which is good. And then later, all the way in 2013 at PyCon, we had Docker, which is where containers started taking off quite a bit. So Docker was able to take advantage of networks, process isolation, and give us a very reasonable isolation approach. The thing to know about Docker is initially it used Linux containers as well, and now it's using its own thing. So this container technology tended to build on top of each other, which is good. And why did Docker take off? Well, this is one hint towards why. We've got this quote from Nigel that says, Docker was the magic that made Linux containers usable for mere mortals. So a big part of Docker is that it's usable. You would want to use it. Whereas containers before Docker, not so much. Okay. So that's our history of containers. Let's talk about how we talk about containers. We've been saying containers a lot. What does it mean to be a container? So container, a running process created from a container image, typically isolated from the host system. So before, when we were running a our Crute example, the bin ls process was a container without an image. Or you could say that the image was the directory that we were making our root. So yes, this is a definition that uses a definition, container image. So a container image is the set of files that are used to create a container. Do you like how these definitions are mutually recursive? Excellent. So in our Crute example before, that folder that we were working in that had all of the dependencies that we needed to run ls and had the program ls itself can be thought of as a very naive container image. And then our ls is that running container. Okay, so let's make that concrete in Docker language. So you haven't seen this yet, but you will. We have a Docker run command, and we specify in that run command what is our container image. In this case, our image is Ubuntu, and this Ubuntu image is a collection of all of the files that we need to simulate having a Ubuntu operating system running on our computer. You can ignore the IT flags. We'll get to that. And then here, we're saying that what we want to run is /bin/bash. So this is our running process. This is our container, more or less. And we're creating it from this container image of Ubuntu. And the IT allows us to be interactive with it. So this opens up a terminal where we can interact inside of this Ubuntu container, and we can ls, and we can run everything that you would expect to be able to run inside of a Ubuntu operating system. Here, very similar process, except, and so we're using the same container image, but what we are running instead is not bash, we're just running ls. Now, ls doesn't have any sort of interactivity, so it just runs, finishes, prints out what it's processed. Okay. A container engine, a tool to create and manage containers, often also manages container images. So in this example, our container engine was Docker, right? We were using it to create containers from images. We can use it to manage containers. We can use it to manage images. Our Docker engine, our container engine is Docker in that example. There are a lot of container engines, Docker being one. Linux containers, which is, yeah, okay, that's around the wrong way. LXC, I think, is another. Rocket is a more recent one. And then the rest are homework, should you so wish. Generally speaking, in this course, we're going to be using Docker for lack of competition, really. Docker has taken over the container space. It's basically synonymous at this point. Okay, so to create these container images. So remember, container images are just this collection of files that we need to be able to run our processes. To create a container image, we need to create a collection of image layers. Now, this is where our layered file system comes back into things, okay? The original Linux containers were, yes, this one directory that you could zip up and pass around and run inside of there. Since Docker, we've gotten a little bit more creative, by which I mean we've introduced a layered file system within our containers, okay? Because a lot of the time we're relying on very, very similar underlying software. So most containers are going to want to start with some sort of operating system like Ubuntu. And if we use a layered file system, then what that means is that our Ubuntu can exist somewhere on disk, and it can be read-only, and it can just sit there. And when we need to read files from there, we can just read files from there. When we need to write to any of the files within our Ubuntu operating system, we can copy them into the layer that needs it. And this means we keep one copy of Ubuntu sitting on our computer, and we can build on top of it. So we need to create those layers. Fortunately, this is no longer a manual process. Instead, we use a build file or image blueprints. Now, this is a set of instructions to tell us how to create a container image. You could do this by hand if you wanted to. It's very unlikely that you'd ever want to, but you could do it by hand. A build file looks like this. So in Docker land, a build file is called a Docker file. And the first thing that we need to specify is what is our very bottommost layer. Okay, where do we start? And this is in itself, this is a container image. So the Ubuntu image, we're building on top of that. You can start from absolutely nothing, no files whatsoever, and this would be from scratch. No one does that apart from demos, as you will see in the containers notes, but it is technically possible. Now, with Ubuntu, it has a whole bunch of files that it uses to keep track of package indexes. In the Docker image, those files are all deleted, which means that every time you start from a Ubuntu OS, you're going to need to run apt-get update before you can install anything. And this is going to download all of the files you need to know where to download other files from. After that, we can then install an example, Cowsay. Has anyone used Cowsay? Yeah, okay, cool. So we can probably run this example. Let's see. What's this going to do? Good. Okay. So we've got our Docker file here. Oops, we've got a perfected Docker file. We'll get to that. And the first thing that we want to do is we want to build it. So I'll explain this in just a second. So Docker build, the -t gives us a name for the image. So Ubuntu is called Ubuntu. Here we're naming our image Cowsay, and the dot says look for a Docker file within this folder, within this context, and execute that, execute the layers on top of each other until you have an image. So we run that. Okay, it's done that. And then we can go ahead and run Cowsay. And we get that. So for anyone who hasn't used Cowsay, this is what it looks like. You can give it some sort of argument and it can spit it out saying it from a cow. So those are our two commands to get this running. Now, this is what our image currently looks like. Down the very bottom, the bottom layer, we have a Ubuntu operating system. On top of that, we have the command that goes and downloads all of the indexes so that we can install other software. On top of that, we have the image that has Cowsay in it, thanks to this apt-get install. And the command is part of the metadata of the image. So it's not a layer in and of itself. It's something that you set so that you say, when this command is run, by default, you should run, when this container is run by default, you should run this command. That's what command is doing. Now, there is something to note about these indexes. So why do we think we have to do apt-get update? Well, we have to do that because the indexes, we don't want to keep them because they take up file space, and that's ideally not what we want when we're packaging up our containers. And we'll see why about the size a bit later. So what we might do is we might run this command, and this gets rid of all of the unnecessary files that we no longer need in our container. Excellent. Is there a problem with this? Yes. Exactly. It won't affect these two. Remember our layered file system. This is all of this down here is read only. So we're still going to have this layer somewhere, and it's going to have all of these files, and we haven't actually removed it, and we haven't actually optimized our size at all. So the reason that we bring this up now is because you will very often see Docker files that look like this, where everything is run on one line, stitched together so that it's the one layer running all of these things. And the result is that this output layer here doesn't have any of the unnecessary indexes. So you will see that a lot, and that's why we're going to mention it now. Okay. So where did our original Ubuntu come from? I'm running a Mac. I do not have Ubuntu sitting somewhere hidden away. Well, technically I do now. But it had to come from somewhere to start with. And that place it comes from is our very final definition in a container registry. Okay. A container registry, definition 5, is a file sharing platform that hosts all of these container images. When they're needed, Docker or whatever container engine you're using is going to pull those images down from the file store and put them away somewhere where you can't touch it, can't modify it, so that you can use it later. So now, if I run any other Docker containers that use Ubuntu as a base, it's sitting somewhere on my computer, tucked away, read only. I can just reuse Ubuntu. Okay. Right. So has anyone throughout this wondered where virtual machines fit in? So sorry, yes? Okay. Let's talk about virtual machines. This is more or less what a virtual machine will look like. You have hardware and you have an operating system sitting on top of that. So this is a type 2 virtual machine, which means that the software that is managing our virtual machines sits on top of our operating system. And this is called a hypervisor. And this manages our virtual machine. So this is one virtual machine, and this is another virtual machine. This guest OS is whatever operating system you happen to install on your virtual machine. This is the file system of that virtual machine, and this is your application. So we're going to say both of these virtual machines are Ubuntu, just for consistency, which means the guest OS and the file system are very likely to be identical. But because virtual machines offer us a little bit more isolation than Docker files, they're not going to get reused. They're going to create a full copy of the operating system and everything needed to run your application. And they're going to, depending on which type of virtual machine you're using, they're going to run reasonably slowly because they're simulating the low-level instructions of this machine, which makes them very slow and very space inefficient. This is what running Docker looks like. In fact, this is not really what running Docker looks like because we've said our file systems are the same. So it's not going to create two copies of this. It's going to share the same file system, and app1 and app2 are going to build on top of that and reuse it. Docker daemon sits over here, manages it. The Docker containers don't have to run on top of the Docker daemon like a hypervisor. It sits to the side and it can manage that and let the containers run independently. Okay, so that's that one. So virtual machines are great for machine isolation when you need to really fence off this machine and let it run somewhere else and you're not really worried about space considerations, choose virtual machine. If you're worried about, okay, how is this particular piece of software going to run on someone else's computer and someone else has 20 other applications running, we only need to isolate just our process. Okay, so let's use containers. So for a quick size comparison, let's say that I'm trying to do vertical scaling. So I want a lot of different Flask servers, as we've seen in the practicals, running side by side so that they can process a whole bunch of incoming requests. So I want 10 Flask servers running on Ubuntu 22. We're going to say these are our size requirements. Ubuntu 22 in Docker is a little bit smaller, but if you're actually using a full Ubuntu image for the desktop, we're going to get to 3.8 gigabytes. Python takes up space, Flask takes up space, your application takes up space. With a virtual machine, we're going to have each of these added together to be the total image size of about 4 gigabytes. So this has Ubuntu, this has Python, this is Flask, this is our application. If I want to run 10 of these, I'm going to have to make 10 copies of this whole image because this is going to be running fully isolated. Fully over here, it's not going to share any files between the virtual machines. If I'm running a container, then we have the bottom layers are going to be shared. So the bottom layers take up also about 4 gigabytes. And we're going to, now this isn't totally realistic, but we're going to say that our app needs to run, needs to be copied across 10 times to 10 containers. So what our total space is for these 10 containers is 4 gigabytes, roughly rounded. Okay, So what our limitation becomes then is our processing speed. Can our computer handle running 10 different Flask servers? But in terms of size, since we're reusing layers, this is really quite useful. So when would you want to use a virtual machine? There are good reasons, and we will see them. So if you're running a completely different operating system, remember that containers are a very Linuxy thing, which means that if I want to run a Windows PC on my Unix machine, I'm going to struggle. So if I want to run a very different operating system like Windows, I'm going to want to use a virtual machine. Now, this has a lot of asterisks because Microsoft is working with container technology, but for the sake of simplicity, if you've got unique hardware requirements, so if you want to run old Game Boy on your computer, you're going to want to use a virtual machine. There is no way that containers are up to that task because it has different hardware requirements. And the other situation where you would want to use a virtual machine is when your security is crucial because it is totally isolated. Now, containers are mostly safe, but if you want total security, maybe split it out into a virtual machine. Why would I want a container? Okay, for containers, running a single application, this is what they're good for. If you have to run a whole desktop, maybe consider using a virtual machine rather than a container because they are designed to just be one running process. They're lightweight, they're fast to start up. These are the benefits. If you've ever used a virtual machine, you know that they do not take a few seconds to spin up. They are fairly slow to get going. And if you're running lots of different container systems on the same machine, you're going to want to use a container because, again, if you've ever used a virtual machine, it slows down your computer fairly substantially because it's a bit of a resource hog. Okay, so if you want multiple, probably try containers instead. I'm not saying that containers don't also slow down your machine because they definitely do, but virtual machines are more guilty. Now, these two technologies are not distinct from one another. They are very often combined together. And a good example of this is if you use the Google Kubernetes engine, which is a way of deploying your containers onto Google Cloud. Those containers run inside of virtual machines that run on top of Google's hardware. So this is a very common use case. You'll see virtual machines and containers used appropriately where it makes sense. Okay, so what are some common use cases for containers? Dependency management, we have discussed this, you saw at the very start. They're a very useful, if brute force, way of managing dependencies. So if you're deploying software, you tend to be nice and you make a little list of requirements for someone to run this on their own machine, and you have your requirements.txt and you have your Maven files. And you capture your dependencies, or at least you try to. Containers are a bit of a brute force way. You wrap up a system that works and you send it off and someone else can download it and run it. So it is useful, but also try to keep a list of what dependencies you're relying on. Continuous integration, right? So if you're trying to run tests and they work on your machine, but they do not work on the CI server, maybe it's time to start considering using Docker so that you can replicate the CI's environment on your local machine, which hopefully brings us to this next point. Well, if you've replicated this environment on your machine and you've replicated this environment on your test server, why don't you just replicate that environment on production? You're going to run into a whole lot less errors if you're going to be running the basically exact same system everywhere. Now, this isn't useful for every use case, but given that we often are just shipping web servers nowadays. It becomes more useful to just stick a container up onto a web server and someone can interact with that container. Okay, and of course, we don't have to just use cloud platforms for this. So as I mentioned, we've got Google Cloud, offers a fairly native container experience. We will see in the practicals and in the assignments that AWS also has a fairly native cloud deployment system. We can also do this on premise. So it's not that hard to install Docker onto a server that you run. And then, so this is how my system at home works. We've got a little server, it sits off in the thing, and whenever we need to install a new application like Home Assistant, or what else do we use? Totally legal Plex streaming things, we can just throw a new container onto that. So you can self-manage your own Docker deployments, which is useful. And you have to do very, very minimal configuration. There's really only 3 to 4 things you need to configure when running a new Docker container, and we will see what they are. Okay, scaling. So we mentioned that containers start up really quickly. That makes them very useful when we have to scale our software. So using the AWS example, the Amazon Web Service, Amazon Shopping example, they get a huge amount of traffic when there's a Black Friday sale or whatever sale they have on. And so they need to spin up more servers to process more requests very, very quickly. If you're using containers, this is a very speedy process. If you're using virtual machines, much less so. So scaling up, scaling down, very useful application of containers. And most cloud platforms have a built-in way of automatically scaling your containers now. We'll get to this, microservices. This is going to be a lecture a bit later. But if you have a bunch of services that implement one thing, so we saw in the tutorial, we've got a CodeGram application, and it's packaged away its image filtering service off into its own little land. We can use containers to keep that all wrapped together and have it not inadvertently talk to other services within our system that we don't want it to. It's a way of keeping those walls up when we want to deploy a microservices type system. Serverless, we will also talk a bit later. I'm not going to try to cover that just yet, but we'll get it. Okay, so Docker. Can anyone tell me the name origins of Docker? There is a hint. Right. Okay. Docker is British slang for a dock worker. These people down here. The whale is a bit of a distraction from the answer here, but dock worker, right? So these are the people who load shipping containers onto and off of big shipping boats. So Docker seems naturally sensible. So we're going to get into the commands that you need to run to build and run things. And so we looked at this a bit earlier, but we have a Docker build command. You will be using this in the practical this week. Docker build says, run each of the instructions that are in our Docker file to create each of the layers that we need. And then that top layer, the accumulation of all those layers, this is now our image. Okay, so if we don't provide a -f flag, it's going to look at the Docker file in our directory. And if we go back here, we can see that's exactly what happened with Cowsay. So we didn't provide a -f. Instead, it looked and it said, okay, there's a Docker file there. I'm going to use that to build an image. The -t gives it a name so that we can refer to it later. You'll almost always want to use a -t flag in your Docker build. Docker run. we've seen this one. We say Docker run and we give it a parameter of the image that we'd like to run. In this particular case, we said cowsay. We don't have to say cowsay. We can say anything we want. We can say Docker run, and you will see these flags. Ubuntu. I did press enter, I did. And it puts us into a Ubuntu container. And by default, this is going to run bash. So we can leave that one. Okay. So -d says run in the background rather than take up your prompt. -p allows us to expose ports. So we discussed that one of the limitations of Crt was that we could access the network willy-nilly. Docker allows us to not do that. So by default, there's no way to talk to any of the network communication happening within a container. -p allows us to say, okay, open up this port so that we can talk to port 80, port 22 inside of this container. Mount a volume. So again, if we want to be able to access a file system on our host machine, then we're going to want to mount it so that we can see that file system from within our container. The rest I'm going to leave as reference for the slide. Docker exec. So we run a container. Sometimes within that container environment that we're currently running. So for example, we start up bash. Sometimes we want to run other commands inside of that environment, and that's what exec does. We will hopefully not see this too much, apart from when something goes wrong and you have to quickly jump into the container to check out the logs or whatever the case may be. Just good to know it's there. Docker PS. All right. Let's hope I didn't leave anything too embarrassing running. If I do Docker PS, yes, okay, nothing is currently running. Good. If I do -a, okay, cowsay is actually no longer running, but it is still there. And that's where this --rm comes from. So this is a flag that says, when this process ends, go ahead and delete that container. I won't need it anymore. And I did not use that for cowsay, so it hangs around. And this can take up a huge amount of disk space. I have constantly run out of storage space on my computer because I forget to remove containers and I forget to remove images. So just be mindful, try to run it with --rm if you don't need to after you run it. All right. Stop does what it says. If there is a running container, you can go ahead and stop it with this command. And we'll do a little demo of that. So let's say this is extraordinarily slow. All right, I entered into bash here. Great. Over here, I can do Docker PS. I can zoom in even. And this says you currently have a container with this ID running the image Ubuntu. The command it ran was bash because that's the default. Now what we want to do is we want to stop that. So we'll do Docker stop and we will grab the ID of this container. So it's not Ubuntu, that's the image. Each container gets its unique ID. And if we do that, we're going to see, oh, is it going to not do it forcefully? We should see it kill, yep, kill our terminal over here. Okay, so we very forcefully got out of there. Now, because we had that --rm flag when we, nope, there we go. When we run that, we can see that container's disappeared. That's gone for good. We don't need it anymore. And rm is, okay, I have this lingering cowsay. It's starting to bug me. It's stopped, but I want to actually get rid of it. And that's how you do it. Go on. Okay. So I have a whole bunch of images sitting on my computer because I use Docker quite a lot. If I do Docker images, I'm going to get all of these lovely images that come from just a lot of playing around. Okay, so you can list off all of the images that you have. There is a command you can use to get rid of them all. I don't know how many of these I need to keep around, so I'm just not going to. This is chewing up a lot of space on my computer. One day I'll delete them. All right, and this is how you would do so. So you've created an image, you no longer need it, or you've pulled an image, downloaded it from a registry, you no longer need it. Go ahead and delete it with this command. And pulling. Okay, so when you run Docker run, the first thing it's going to do is look on your local file system. Do you have this image somewhere? Have you already downloaded this? Docker pull is then going to, so if it can't find it on your host machine, it's going to look at the Docker Hub container registry and see, is it up there? Is there a container up there that we can look for and pull it down? If it is, it's going to automatically run Docker pull for you. So you don't often need to manually pull a container down. Docker run is more than likely going to find it and pull it down when you need it. Docker push, this is the reverse. You've created an image and you need to put it in the Docker Hub registry. You do it like this. And those are all of the Docker commands. Any questions? Okay, we think we're going to be ready for the practical session then. Great. One thing for the practical session, install Docker before you get there. I don't want to spend the first hour trying to install Docker. Okay, now for some fun. So what can you use Docker for? One thing you can use it for is Structurizr. So I'm going to spoil Richard's lecture just quickly. And I'm going to go and go up to here. Sorry, this is painfully slow. Nope, I'm too. And we're going to go in here. And what we're going to do is run this command. So let's break it down. We've got Docker run, obviously. We've got IT. So this is a command that you often want to run because it allows your terminal to speak to the Docker container, which you may not think you always need, but eventually you're probably going to want to Control C and kill the process that's running. So generally keep this flag around. Same with RM, save yourself the disk space, just always use RM. -P, so we want to be able to talk to the code that's running inside of this container. And we're going to do that through network communication. And what this is saying is port forward port 8080 on our host machine so that we can talk to port 8080 on the inside of the container. So presumably this container is going to run something that listens on port 8080. And that's the goal of this one. Now, -V is volume mount. So what this says is take my current working directory and map that to, or mount that to the directory /user/local/structurizr. And why do we do that? Oh, there we go. Okay, so this is an example of it pulling it down. So I don't have structurizr sitting on this computer. Oh, and we should note, this is the image that we want to run. It's identified it's not on the computer, so it's going to go off and pull it down from Docker Hub. Slowly but surely. So you can see it's doing both download and extracting. That's because Docker layers are just compressed folders. Okay, and now we're getting some output, and this is from inside the container. This is going to be echoed out to our terminal so that we can see what the process running inside it is doing. And what it is doing is it's starting up a little web server so that we can go ahead and talk to it. And we're going to do so very, very slowly. And pop that in there. Okay. So let's hope that's had enough time to open up. Maybe. So if we go to port 8080 of our local machine now, it's going to port forward that so that we can talk to whatever is serving things on port 8080 inside our container. And shockingly, we have an application called Structurizer, which is the name of the image that we downloaded. So yeah, okay, this looks like it's working correctly. Now, I didn't have to go install any dependencies on my local machine to run this. I don't even know what type of software it's using. I don't know what the website server's built in. It's beautiful, okay? This is lovely for me because I don't like installing random dependencies onto my computer. And we can see that this is, yes, some sort of diagram software that Richard is going to tell us all about shortly. Now, I will leave the other two examples for now, just so that I give Richard plenty of time for his component. But you can run a lot of things with this. So the other example was going to be run a, what is it? GitLab. So you can run GitLab on your computer, then you can go and have a locally hosted GitLab that you can play with, or you can put this container out onto a server, play with that. The other example was, of course, a Doom installation. So if you've got a piece of hardware, someone's going to try to run Doom on it, and Docker can run Doom and then forward those to the browser, and it's weird and wonderful. So I'll put those into the slides and you can go ahead and run Doom if you want. All right. One very last thing, because you are going to be using Docker Compose in the practicals, so we should probably discuss what it is and why. So if we want to have multiple containers working together and talking to each other, we probably don't want to keep running these Docker run or for this to this Docker run for each and every container that we want to be using in our system. So yeah, exactly that. We don't want to remember all of the commands, first of all. Sure, you can script it. So let's do that. We're going to have some tedious Docker run -p and then the port of that container and then the name of that container and mount the right directories. Okay, fine. We're going to script that and it's going to look like this. Okay, so when I run this script, it's going to build my two custom containers, front end and back end, presumably having our front end code and our back end code. And then it's going to start two containers. It's going to use the front end and back end images. It's going to pass in some environment variables to both of these images. It's going to mount our front end directory to /app so that we can update the code for the back end, for example, on our computer, and it updates inside the container. And then we're going to open up some ports so that this code can talk to the outside world. And then we're going to run a reverse proxy so that we can just go to port 80 and it's going to route based on the request that we made to either the front end or to the back. We don't want to have this script for every single project that we run. And we would, because this is a very common way of working. So what we do instead is we use Docker Compose, and Docker Compose looks very much like our scripts. Okay. So what we have is we can specify that this service, this container, is going to be built from a particular Docker file or from a particular Docker file within a particular context. And we do that with this. So this is specifying it using YAML. And we say, yeah, okay, front-end service built by this Docker file. We're going to open up some ports. Okay, cool. That's exactly what we were doing over there. We're going to mount some volumes. Cool. Exactly the same. And we're going to configure some environment variables. Now, the important thing about this is that this means we don't have to worry about tearing everything down. So to put this up, all we have to do is say Docker compose up. It's going to find this Docker compose YAML file and create any of these containers, these images if they don't exist, and run them. And Docker compose down. So this is really the useful part, because otherwise it would be quite a pain to go and find all of these running Docker containers and manually kill each one of them. So Docker compose down takes care of this, which is lovely. PS does the same thing as Docker PS, but for only at the containers we care about. Logs looks at the logs of these containers. Exec, the same thing as Docker exec. And then builds. So eventually, initially, we're going to have to build some of these images so that we can then run them. All right. In the practicals, this is going to be you deploying your containers. We are going to be working with Docker. We are going to be running the to-do application inside of Docker. So you're going to get quite familiar with all of these commands. You can use these slides as a reference if you want. Okay. I'll leave it there. Richard can take over and teach us all about microkernel architectures. Let me know if you've got questions.